Oh, there it goes. Good. Got nervous. I thought it froze. Here we go. So this is another example of this AC factor. So we have this thing we want to factor. And really, it's just like before. This GCF is going to be 1, right? There's a non-zero constant term, okay? And a coefficient is 1. So we have a non-zero constant term, right? So we can't factor out x, so our m is 0. A coefficient is 1, so our GCF is 1. And now, just like before, by comparing the two with ax squared, comparing the polynomial with ax squared plus bx plus c, right? Notice we get a is 6, b is 1, c is minus 7. I wrote addition here. You really don't have to write addition if you don't want to. I just wrote it here to remind us that you have to include the negative when getting your coefficients. And in this case, your constant term. You always include the negative, okay? I've seen students in the past, from minus 7, they would say, oh, well, c has to be 7. But that's not right. You always include the negative sign. So just like before, right, we get a times 6. 6 times negative 7, which of course is negative 42. Our b is 1. So going back to our method, we want two numbers then whose product is negative 42 and the sum is 1. So we're just using the AC method. We want two numbers whose product is this, but the sum is 1. Well, hopefully from here you could probably guess that the numbers are 7 and negative 6. I mean, that should be easy to see that their product is negative 42. And if you add 7 and negative 6, you're going to get 1. So what do we do next? We're going to replace 1 with negative 6 plus 7. I wrote negative 6 plus 7. You could replace it with 7 plus negative 6. You'll see this actually works out by chance to be easier. If you did replace this with 7 plus negative 6, it would get a little bit tricky. Not terrible though. It just you would just have a little bit more work to do. Mostly because the second and fourth term would not be the same. Here they are. Okay. But either way, if you proceed correctly, you'll get the right answer. So anyway, replacing this with negative 6 plus 7, right? And then of course, as before, x, here, let me draw it in. X will, right? We distribute, as you can see. That's how we get this. It's also easier because we have addition here in front of the third term. Just makes it a little bit easier, but now we can form our groups. And so now we have to handle each group. Now from here, it should be easy to see what the GCF is, right? The smallest exponent of x is 1. And 6, and that should be a negative 6. Let me just fix that. 6 and negative 6, right? Their greatest common factor is 6 itself. You know, hopefully you can see that. It's pretty easy. The factors are the same actually, 1 and 6. So the GCF for this thing is 6x. So what do? We factor it out. And that's what we're doing here. So from the first group, we get this. Now we must handle the second group. So for the second group, 7x minus 7, we're missing an x here. So in the GCF, that m must be 0. In other words, the GCF is only going to be a number. And it's just like with the first group. We have 7 and negative 7 here, right? Well, the greatest common factor of 7 and negative 7 is 7. You know, they actually have the same factors. So the GCF here is 7, and we just factor it out. Okay. I know we have like about 4 minutes left, so I really want to finish this. Okay. And so putting those in, you can see that we have a common factor of x minus 1. So we factor that out. Right? You pull it out, you divide to see what's left. Divide into each term, and you get this. So that's what we get. If you replace the x here with 7 minus 6, you can do that. That's fine. I mean, it's not much more work, but it's just a little bit more, but not much. All right, so, okay, let me just state now some vocabulary associated with factoring. I mean, really, it's just like with integers. Whenever you factor a polynomial, there's always two ways to factor it. That's basically when one of the factors is 1 or negative 1. And then the other factor, of course, is the polynomial or itself, or it's negative, excuse me. You know, it's just like with, integers. But those factorization, we call them trivial for a reason, mostly because they're not going to help us. You know, when we factor, the whole point of factoring is to make the problem easier, take it apart piece by piece. But those trivial factorizations, they're not going to accomplish that. And just like with integers, there are certain numbers that you can't factor besides the trivial one. And so there are polynomials. The only way you can factor them are the trivial ones. We say those are irreducible. And you can get examples such as this where that AC method doesn't apply, meaning this. There's no factors of A times C that add up to B. And that's a little general, I know. So here's something a little more specific. You have these here. Assuming A and B have no common factors except 1. And A and B are non-zero. So these are irreducible. In particular, if we take A to be 1, right, then you get irreducible polynomials. And that's what I'm saying here. So if you take x plus 1, x plus 2, whatever, or as we saw earlier, the sum of 2 squares, that's irreducible. Again, you can't break them down any further. And if it's not irreducible, we say it's reducible. Again, it's similar to the integers. That's what I'm trying to say here. And it turns out for any polynomial, you could break it down into a product of irreducible factors. Why can we do that? Well, that's beyond the scope of the class. In Math 104, I mean. But that's what it means to factor a polynomial completely. So hold on. Okay, so that's actually it for